In the preceding video, I talked a lot about how probability relates to statistics. Now let's tie the machine learning term into the mix. So Bayesian statistics has today really become a type of machine learning. And we use it where sample sizes tend to be not very large. And by very large, I mean, say, millions of observations or more. We'd also use Bayesian stats where we typically have evidence for priors. So these priors are initial parameter values in our model. So they kind of give our model a starting point for the values that we think they should be learning. So this could be based on prior experiments that we've run or some other kind of information that we have. So we can start our machine learning model off with some helpful information before it starts training based on data. Probability concepts, more generally, are ubiquitous in artificial intelligence, including machine learning approaches to AI. And this is a major focus of the probability and information theory content that we're covering right now in the first half of these live lessons. So, for example, uncertainty is typically involved in mapping a machine learning model's inputs to its outputs. And uncertainty is a key thing that we can model with probability theory. Machine learning models tend to output their results as probabilities. So if we feed in a picture of a hot dog into a computer vision model, then that could be, say, a deep learning convolutional neural network. And that neural network might output, hey, there's a 98% chance that this is an image of a hot dog. So models output in the language of probabilities. And with statistics, we can confidently compare model performances. So we can use probability theory combined with statistical inference to compare, hey, I get this result with one model, I get this other result with another model. Is that difference random? Would I expect that kind of difference to happen by chance alone? Or is the difference between those two model performances statistically meaningful? And finally, some machine learning models are themselves stochastic. So they're non-deterministic. And all that this means is that the models themselves aren't going to give you the same answer every time you run them. You might put the same training data into the model on two separate runs, but you get back a slightly different result, or in some probably rarer cases, even a widely different result. And that difference in results is stochasticity or randomness, non-deterministic nature. And again, probability is the underlying core idea when we have ideas like randomness, stochasticity, uncertainty. That is where probability theory really shines. So a really important question that you might be asking yourself when I tell you things like this about the randomness in machine learning models, you might ask yourself, why can't most artificial intelligence systems, like machine learning systems, be certain and be deterministic instead of being probabilistic and stochastic? Well, one really big reason is that the process being modeled is itself stochastic. So even the process that we're modeling has some randomness in it that is non-deterministic. So for example, games of chance. We can't build an AI model that can predict whether a fair coin is going to flip heads or flip tails, or whether you're going to roll a 7 or a 12 when you roll 2 dice. Human behavior in general is stochastic. We are not deterministic systems. And so, something like the stock market in particular does not behave in a deterministic fashion. So if we're going to model a stochastic process like these, then we can't have a certain and deterministic model for that. A second big reason why we can't have a certain indeterministic AI systems is that model inputs are typically not comprehensive. So for example, if you have a self-driving car that is perfectly programmed somehow, that if it has all of the information it needs about the road, it couldn't get in a car crash. But there will be model inputs that are not available to the car crash in some circumstances. So for example, if the car is going at a particular speed around a tight curve, a high speed around a tight curve, and there's been a car crash around that curve, there's no way that the cameras or LiDAR systems on the vehicle can detect that crash. And so there are incomplete model inputs in that situation. Let's say that you're building a model that is predicting whether a candidate is going to accept a job that you offered that candidate. Well, the model wouldn't know if the candidate has an offer from another employer, for example. So another reason why the model can't possibly determine this answer conclusively. And then the third big reason why most AI systems can't be certain and deterministic is that the model itself is typically incomplete. So even if the process that we were modeling isn't stochastic, so the process that we're modeling is totally deterministic, and even if we had all of the model inputs that our model would need, the computational complexity of the perfect solution is often astronomical. So, if there's some board game like chess where we have all of the information on the board, we have complete information, the model itself can't possibly work through all of the moves that it could take and which one is the exact right answer. So in a lot of cases, we have to rely on a model that doesn't work through all of the possible solutions. It's incomplete. Another reason why we need an incomplete model is because the modeling approach for solving the problem perfectly is unknown. We don't know how to build that model. And another reason why we would use an incomplete model is that building the perfect model might be unreasonably expensive. It would require way too much data or way too many model parameters. It would be way too expensive to run on cloud infrastructure, and our company would go bankrupt, even though it gives perfect answers to our clients. So as a final point on this, generally all three of these things are true on any model that we build. All right, so we've already covered a lot of introductory probability theory. We've talked about many of the key terms and concepts in probability. We've linked probability to other areas of study like statistical inference, machine learning, and artificial intelligence. Up next, in the next lesson, I have even more detail on how probability works.